Hey guys, welcome back to the channel. Today we'll be doing episode number 8 of creating a custom ray tracer in C++ and Unreal Engine. In the last episode, we actually implemented our dielectric material or a glass material using Snell's law and a refraction function. Today we'll be implementing a light function, so emissive material, so to speak. A similar kind of thing to Blender, we have a emissive color and then we have emissive strength. So if you have an emissive color and crank the strength all the way to 1, your normal object now becomes an emissive object, that is emitting light. It becomes a light source. So that is what we'll be modeling today. In fact, it's quite simple actually because of the nature of the program. It's a brute force ray tracer, so we don't have to add additional um, functions or additional uh, dependencies, not dependencies, but additional logic, right? We don't have to add a lot of new logic. We can just create a emissive function that returns the color of the light and then put it somewhere in the ray color code to return the light's value when we hit it, right? So let's actually get into coding. Let's open our hittable.h first, and let's declare a boolean value to check if the object is in fact a emissive object. So let's come below the B metal and then implement a boolean value saying emissive, right? And we'll set it at false because not every object is going to be emissive. And we'll also need to declare an emissive strength. So let's come down and copy the fuzz here and put emissive strength, or th rather, and it's going to be a default of 1. And we'll also need to define an F color for the light color itself. So let's copy the material color and then paste it right below the emissive category, and then let's call it emissive color. At default it's actually going to be 1, so let's actually set that. Let's say F color white. Okay, and let's declare a emission function. F vector emission, and then for parameter it's going to be empty because all we are doing is returning the color of the hittable object that is of type emission or emissive or emitter, so to speak. I think emitter is the right word to use here. So let's actually create the definition. Right click, create definition, and let's come into our emissive function, get the F vector component of the light color. Let's say emissive color color.r emissive color.g and emissive color.b, and then let's run a check to check if we are a emissive object. P emissive. If we are, then return the color of the light. Emissive intensity multiplied by the light color. So that should be pretty much it. And if you're not an emissive object, we just return a black color, right? So black color, adding 000 to an existing color pretty much means no change to it, right? So let's do that. And we should have all the things we need to actually call the light source. So let's actually go back to a ray tracer CPP. In here we can just come below the attenuation and say F vector light color, or light pretty much, and then let's call the hit actor emission. And once that's done, let's actually come to the return statement and add the light to the existing color. Light plus color into a color. That should be pretty much it, but let's also implement a logic where we actually determine the strength of the background color on the material itself, right? So how much effect does it have on the materials on the scene? In order to do that, let's come back to raytracer.h and define a background intensity. Let's just name it intensity, right? And at a default value of 1. Let's come all the way down to the return BG color value and then just multiply it, right? BG intensity multiplied by the background color vector. Now if we build this, we should have a light source in the making. So we have the build. Let's minimize and come back to Unreal Engine. And let's go to our blueprints and grab our hittable plane, drag it into the scene, bring it all the way here, reduce the size to be somewhere 4, and just about the monkey and the ball. Something like that should work. And then let's turn on the emissive boolean and then add a emissive color to be white at default, right? We can actually change that as well, but we don't have to. In fact, let's actually try changing it to yellow. I think it will go nicely with the red flow. So let's position the camera and start rendering pretty much, and save everything before you run it. Yeah, so we have a light function going on in our ray tracer. We have it casting shadows as well. So let's actually see the shadows being more prominent when we actually change the direction of the light source. So we have directional shadows as well. So let's stop that and actually angle the light source to be in certain directions, maybe like this a little bit, and also increase the emissive strength to be kind of 2, so that's double. And then another thing we might have to do to see the light source be more profound effect is to reduce the background intensity. So let's come back to our ray trace manager and then decrease the background intensity to be 0.5 or 0.4, and then let's try running that. And yeah, now we can see the more distinct light effect. We have a shaded part in yellow on the sphere, and we can also see the absorption of light and refraction of light through the glass actually. So we can see a little bit of light leaking through, and we also have the directional shadow, which is a trademark of directional light here. And we can also see a shadow in the light plane itself. So along the light plane we can see some shadows. So that's pretty much it for the light. It looks awfully simple because we have our core components of the ray tracer actually supports the implementation of light source to be that simple. So what actually happens is when we're calculating the color for a point, let's say we have a surface and we are shooting a ray and it hits a point. Let's name this point A, and we calculate the color of this point by shooting another ray outside, right? So we are scattering the ray to calculate the color for this point. So let's say we scatter this ray in a random direction, so that will be a diffuse material. So it shoots in this direction and heads all the way to infinity. If it does that, if it goes all the way to infinity, then we'll say, okay, let's sample the sky color, which is the background gradient, right? But what if it hits a light object like we have here? So let's say our light object is positioned here and the ray hits the light object. Now obviously we had a calculation for the emission function. So if it is a light object, then we return the color of the light source instead of the scatter function, right? We don't scatter it anymore, but simply say, okay, we don't have to do anything, just return the emission color or emission color. And so that white color is being sampled back in the recursive call, it goes down, and this point A is now added that color value. And that's why we see the light function being so easy to implement, because the very nature of ray tracing allows that to be that simple. So I think the light functions are pretty easy and done. Talking about easy, another function we could implement, or another feature I forgot to implement in the last episode, where we defined our light sources, or not the light sources, the glass materials, right? I think I'm being forgetful now, but or the metal materials. In the video where we did metals, I actually said we'll define a frosted glass material using the same method as creating a rough metallic material. So let's actually go ahead and do that as well. Let's come back to our Visual Studio, and let's come back to our hittable object and then declare a function or a parameter. Sorry, I keep forgetting a lot of things today. So let's actually come and copy the first value and then bring it down and say frost and add a default value of 1. That's fine. Let's come back to our hittable.cpp and come to the scatter call for the refract function, and all we have to do is add the multiplier frost multiplied by the same random unit vector. Now if we build this function, we have a frosted glass look. So once that's done, let's actually come and make the monkey a little bit high frosty, or a high amount of frost, because if you have low amounts of frost, you will see the noise add up a lot. So you have to crank up the resolution and the sample count, which I'm not going to do today here. I might do it in the final render just to show the quality, but for now let's actually put it really high, so like 1.2, and then let's try rendering it. We should see that nice frosted glass look like you see in your bathroom and stuff, right? So yeah, there you go, we have a frosted glass look. Now as I said, it's a lot noisy because the sample count is low, but we can see a little bit of transparency here, like we can see a little bit of red leaking through, and also over here, and the eyebrows, we can definitely see that frosted glass kind of vibe, right? So let's stop that. And another thing I want to try to emphasize here is the refraction of light through the glass material itself. It's pretty cool because here we have a simple program, not a lot of code, but we are actually recreating real life physics to an accurate degree, right? So the emissive function, let's actually, it works best on glass, sphere objects. So let's actually take this sphere object and make it glass, or glass not emissive, and then reduce the frost to be 0 pretty much. And what I can do is bring the the emissive object a little far away to get that more pronounced refraction look, maybe that far. And if I come here, let's actually move the monkey away and let's render this out. Yeah, so that is what I'm talking about. We have this nice refracted light that actually goes through the sphere and gets distorted by the IOR. The IOR for this ball is quite low, I think. So let's check how much we have. Hittable ball. It's quite high actually, it's 1.2, but yeah, I think it has to do with the noise. Yeah, but it's pretty cool, right? Well, that's pretty much it for the ray tracing series. This is probably going to be the last official video on the series. I'll actually try to make some extra videos on depth of field and volumetric fog if it gets a lot of likes. So if this video gets a lot of likes, I will definitely go ahead and make it. Another thing I want to point out is I have a Patreon. So if you want the access to project files and source codes, you can actually support me there. It really does help me a lot and help me stay motivated to create more videos on the channel. With that said, thanks a lot for watching, and I will see you guys in the next episode.